Okay. Okay, now we can start. Yeah. Good afternoon, everyone. I am Edi Tribaskoro, and I'm your host today in this series. We are delighted to welcome you to our Mathematics Distinguished Lecture Series. Today is the second edition from the third year of this Mathematics Distinguished Lecture Series. We are very grateful to welcome the Dean of the Faculty of Mathematics and Natural Sciences, Institut Teknologi Bandung, Professor Wahyu Sri Gutomo, and we also thanks for his continuous support to holding this series. And today, we are honored to have with us Professor Dr. Kuntjoro Adji Sidarto, one of the great mathematicians from Indonesia. Professor Kuntjoro is a professor from the Industrial and Financial Mathematics Research Group, Faculty of Mathematics and Natural Sciences, Institut Teknologi Bandung, Indonesia, and his research interests are very broad, covering various important fields in mathematics, including optimization, financial mathematics, computational mathematics, and all fields related to optimization. And we can say that he is a pioneer in Indonesia for exploring new methods and directions in optimization and computational mathematics. And he's our senior professor who has extraordinary dedication in education and student supervision as well. In this today's lecture, Professor Sidarto will discuss about solving nonlinear equation system using spiral optimization algorithm with clusterings. The talks will be chaired by Dr. Novriana Sumarti. I would like to mention here that the audience are not only from Indonesia, but also from neighboring countries. The number of people who registered in this event is about 106 people. And they are from Philippines, Thailand, Japan. We are honored to have Professor Shimizu from Japan, the president of the Japanese Math Society, and also we also have people from Korea, and of course, the majority from Indonesia. This Mathematics Distinguished Lecture Series is organized by the Department of Mathematics, Faculty of Mathematics and Natural Sciences, Institut Teknologi Bandung. And now I would like to invite Professor Wahyu Sri Gutomo, Dean of the Faculty of Mathematics and Natural Sciences, to give an introduction remark. Professor Wahyu, time is yours.
Sorry, you have to...
Sorry, Professor Wahyu, can you unmute the mic?
Oh, yes.
Okay.
Okay.
Yes.
Okay. Thank you. Thank you, Pak Edi. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Unmute again. Prof, are you, the mic still off?
Okay, thank you. I'm sorry.
Yeah.
Good afternoon, everyone.
Good afternoon.
On behalf of the Faculty of Mathematics and Natural Sciences, Institut Teknologi Bandung, I would like to say thank you. I want to express my sincere gratitude and highest appreciation to all of you who has been constantly attending and making this distinguished lecture possible. Of course, thanks go to Professor Eddie and his colleague from Department of Mathematics, Faculty of Mathematics and Natural Sciences, who spend many time and efforts to make this continuous event happen. And I would like also to hope that all of you can gain or obtain benefit from these serial lectures, distinguished lectures, and you have also time on or an opportunity to sharing ideas and communicating some thoughts that is important in development of mathematics in Indonesia and also in other places. And I would like also to thank all the participants from Indonesia and all of the countries who are participating this event, and to the speaker, Professor Kuntjoro. Thank you very much for your dedication all these years. You have been inspiring us with your thoughts, your love in mathematics. So please do not stop, and please also accompany us always. Thank you very much, Pak Edi. And that's all. Please have a good lecture. Assalamualaikum.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Professor Wahyu. And now, before I hand it to Dr. Anna, please, we have a photo together. So in that case, I would like to invite Ridwan to share us, to lead us to have a photo together.
Yes, please.
Yeah.
Good afternoon to everyone. Please open your camera.
Okay.
Okay, I will still wait for everyone to open the camera. Okay, I will start take the picture. Wait, there's still. Okay, I will start taking the picture. Please give us your best smile. Okay, 1, 2, 3. Okay, once more, wait a second. Okay, 1, 2, 3, smile. Okay, it's finished, Pak Edi.
Okay, terima kasih Ridwan. And now I would like to invite Dr. Anna Novriana to share this session, these lectures.
Thank you very much, Pak Edi. I will now share my presentation first. Okay, good afternoon, everybody. My name is Diophantine Sumarti. I'm the moderator here. I'm delighted to introduce Professor Kuntjoro Adji Sidarto as the speaker of this event. Uh, if I can say that Professor Kuntjoro is our hidden gem because he is very low profile, but his hard work and helping hand in research and education in ITB. He talked about solving nonlinear equation system using spiral optimization algorithm with clustering. So I say first about the, sorry. Professor Kuntjoro Adji Sidarto graduated from Institut Teknologi Bandung with bachelor degree in 1976 and got master and PhD degrees from Université de Montpellier, France in 1978 and 1981 respectively. He got awards, several awards. In 2009, he got Satya Lencana Karya Satya, his 30 years in service award as a civil servant. In 2016, he got 35 years in service award from ITB, and in the same year, he got ITB Innovation Award at ITB anniversary ceremony. He has done pioneering works so many times. Some of them are following. In 1990, he was involved in developing the STT Telkom curriculum. This is a famous private university located in Bandung. And in 2001, he was involved in developing OPNet, optimization of pipeline network. This is the research consortium among oil and gas industry. And in 2003, he and the late Dr. Muhammad Samsudin, the late Muhammad Samsudin, first introduced financial mathematics in mathematics, ITB mathematics curriculum. So he is one of the founding fathers of financial mathematics, especially in ITB. The book that has been published is about financial mathematics and computational financial mathematics. And the research topics are very wide-ranging. It is from optimization, mathematical modeling, financial mathematics, biomathematics, petroleum engineering, mining engineering, environmental engineering, and etc. These research topics are reflected from the PhD student research that he has been as a supervisor or co-supervisor in ITB. And if I look for the Google Scholar, it hits 214 papers. And in September, we will organize an international conference on optimization and financial mathematics. And it is the tribute for Professor Kuntjoro. It's the remark of his end of service as the civil servant. That's all my introduction to Professor Kuntjoro. Please, you can begin the presentation.
Okay, thank you. Okay. Good afternoon to all of you. I would like to present my talk. This title is Solving Nonlinear Equation System Using Spiral Optimization Algorithm with Clustering. This is an outline of my talks. So might be some topics, but maybe not all. I would like to start the introduction. What is new? Okay. We see that in our episode, we see that optimization problems in engineering are often highly nonlinear problems involving many different design variables under constraint. This is the specific problem in engineering, naturally. Such nonlinearity often result in multimodal objective function. Hence, we see that local search algorithms such as air climbing or steepest descent method of solution are not suitable to this. Thus, the global search algorithm should be used to obtain optimal solution. This is the problem if we concern about multimodal optimization. Many metaheuristic algorithms have been developed to perform global search. They are constructed based on the analogy of natural phenomena, such as biological evolution. We see that this a great example is genetic algorithm, bird flocking and fish flocking. This is the start on the particle swarm optimization and etc. So, Bismillah. Tidak berubah. There's a problem, Yes. Okay. So, okay. Yeah. Sorry. There's my problem in my computer.
Oh.
Yeah.
It's working.
Done. Yeah. Yeah. So, optimization problem in engineering are highly nonlinear for many different constraints. In local search, and also many metaheuristic algorithms have been developed so that perform global search. They are constructed based on natural phenomena, like synthetic algorithm, particle swarm optimization. Now, what is about the algorithm, heuristic algorithm? So we must talk about this term. So let us assemble definition. A heuristic algorithm is a rule of thumb for solving a problem. It is not necessarily based on precise mathematical theory and is not guaranteed to give an optimal solution. But rather, a heuristic algorithm is used because it can give very good feasible solution very quickly. This one. So this is a good one. A metaheuristic algorithm is a heuristic algorithm in which each step is itself a heuristic. So this is a sample definition of metaheuristic and heuristic algorithm. We have two characteristics of metaheuristic algorithm. That are first diversification and intensification. And the diversification phase, searching for better solution by exploring wide region coarsely. And intensification, we want to searching for better solution by searching around a good solution intensively. Diversification in the early phase during a search can find region, this is having a high possibility that better solution exists. While intensification in the latter phase can intensively search for much better solution in the region found in the early phase. So there is a combination of diversification and intensification phase. Yeah, recently, about 10 years ago, maybe 12 years ago, A new metaheuristic search algorithm called spiral dynamic optimization has been developed by Tamura and Yasuda of Tokyo Metropolitan University. Preliminary study at that time showed that the effectiveness on the method compared to other metaheuristic such as PSO. So this is the spiral illustration. One of we have three figures. One of them is a spiral galaxy. So we see a spiral pattern in nature. So we start with the spiral dynamic. Yeah. Okay. Yeah. So let us make a rotation through an angle theta. Yeah? So for example, if we have a point x1 k x2 at time k, and we perform rotation with a matrix of rotation, cos theta minus sin theta, like that. If we perform rotation, we center at the origin, we see that if we use, for example, this one is theta equal p over 4. So we have see start k equals 0. We start from this point. If we perform a rotation counterclockwise with theta equal to p over 4, we arrive at this point. And at k equal to, we arrive at this point, and so on. After at such, we found when we start. So this is the problem. We can modify if we have theta equal p over 2. So this is the trajectory. K equals 0, 1, 3, 4. Yes, we run as well. So this is the typical rotation method. We center at the origin. Okay. Sorry. This. There's a problem. Okay. Sorry. Yeah. Now we multiply our rotation matrix with diagonal matrix. For example, this one, with a diagonal matrix 2 by 2 is a diagonal at with R, where R is between 0 and 1. So the result is this in the figure. So start from k equals 0 at k equal 1. We see this one. So first perform the rotation under this one, and then shortening by the factor R, where R is between 0 and 1. So this might be shortening. So if you start from here, this is the origin R, then so we shortening at k equal 2. So we have at the end we have a spiral trajectory until we found the origin. So this is a spiral algorithm with center at the origin. If we use this is the theta equal p over 4 and r equal to 0.95. If we use theta p over 4 and r equal to 0.9, we see that this is the spiral. So we see the difference. Here if we have p over 2. So this is the trajectory. So we have the spiral converging to 0, to initial velocity. Okay. Yeah. Spiral model generate a point converging in at the origin from arbitrary initial point x0. So this is one. So we can write this equation in matrix vector form. This is the S2 xk. This one. S2 is equal to multiplication of diagonal matrix R and rotation matrix S. So this is S2 R theta. By translating the origin toward arbitrary point x star, we have a spiral model with center at x star. So this is the result of translating the origin to the point x star. Yeah, we have this one. Yeah. The trajectory will converge to what x star because this is we consider say k is xk minus x star. Yeah, so we have a recursive relation. Yeah? There will be this is a conversion matrix for the origin. Yeah. Many metaheuristic methods such as GA, PSO, genetic algorithm, particle supermodulation, and uncolony optimization use multi-point sets with interaction. The multi-point set using spiral model is formulated as this is the multi-point set. This is the matrix S2 minus this. This is center of rotation. So x star. So with the common center x star set as the best solution among all search points during a search. Thus x star becomes an interaction. So this is our multiplier x star. Yeah. We have here we have for example the first spiral we have 25 steps, and the last spiral 25 steps. So this one. So you see that we start from x0 10.10 and x star the origin x 4.6. Yeah, this is 4.6. The origin of the spiral. And this is the last 25. So we have performed 50 iteration. Okay. Now this is now we start about what is the algorithm developed by Tamura and Yasuda in 2011 for a minimization problem. The algorithm is relatively simple. We have an input m. This is the number of search points. Greater than 2. Theta. This is the rotation. The rotation matrix like that. And r. This is the radius, the radius spectral, radius spiral. And Kmax is maximum number of iterations. So we have a process generate randomly initial points, xe, and 2 vector in 2 dimensions. So in the visible region, set k equal to 0, and after that find x star as x star equal to x e0, where it is minimum. X star will give the minimum among the value of f among the m points. Xe e1 under m. So we search the index e as xe such that fx is minimum among m points. So it is index point. After that, we update the new points on the spiral. This is the updating spiral. This is the spiral transformation. So we see with the center at x star. And so at time k, become the new point at time k plus k, at time k plus 1. We obtain another point. Start from m points, and we obtain another m point at k plus 1 iteration. A new point. And then we update the x star. We first from this point where we have found that minimum of f is at k plus 1 steps. So this one. And continue until k equal to k max. Terminate. Otherwise, k equal k plus 1, and so return to step 4. So update. So we have spiral optimization. Output x star as a minimum point of fx. This is one. So we have an example. For example, we have 20 points. And so suppose that we have among this point, we have f as at this point minimum. So after we stop that, we perform a spiral transformation. After 10 iteration, we see that the point will transfer to this point as a minimum. And the other point is we have shown another distribution of point at, and after that we continue. So we have another point as a minimum. You see that we have at this point. This is the minimum among 20 points. Continue. This one. So we can another position. So we search the another one. Okay. So this one. And that's under the conversion. Yeah. Okay. So this is conversion. So I would like to show the example. Suppose that we have this function, and in the region of -4 under 4. If we have input parameter, m, this is the source point. We have 30 and r equal to 0.05 and k max equal to 300. So theta we obtain using spiral optimization that at the end at k max we have that x1 is equal to -2.9 and x2 is equal with f equal to -78. This is the minimization. And this one is a graph of the function, this function, f, in 3 dimensions. So this is, and the lower part is contour plot diagram. So we see that the minimum will start at this point. So we see that this is the blue, dark blue. So this is the local minimum, and this is the maximum. So we see that one. So yeah, corresponding to this position. So we can see that this must be here. So I would like to show you that I will set 50 point and start with this one. Okay, I would like to show you the module. So we have distribute this point randomly, and hopefully we have seen that this is the lowest point among these 50 points. And yeah, basically this one. So we start with the one. So this is the process spiral. So and we convert to this point. All point will convert to this minima. Okay. Yeah. Okay. Another point is restriction function. This is a multimodal function. We want to find the minimum. And okay, and this is the 2-dimensional version. And 2. This is and the lower vector is contour plot diagram. And this one is the function. The graph on the function is okay. So if we start with input m, we start with 100 points and k max 200 and r equal to this one 0.95 and theta equal to v over 4. We arrive at output x1 almost 0. So we fit and f is this one almost 0. So we see that our problem will be converted at the origin with f equal to 0. So we see from this figure in 1 dimension, see this one. The minimum is at x equal to 0. In 2 dimensions also x and the origin. But if okay, how about higher dimension? For example, we have 3 dimension, 3-dimensional spiral model. In 3-dimensional, we have 3 rotation matrix. First, a rotation in the x1, x2 plane, and in the x1, x3, and x2, x3 matrix rotation. So we see that this is the equation of the spiral model transformation with r equal to this one. With r is rotation matrix in 3 dimensions. So this one. This is a picture of we have 3 dimensions. We start from then this start from this one on this point and perform transformation with theta equal to p over 2 and r. So we get the trajectory from this one with this one and this one. Yeah? So and at the end we'll convert to the 0. Yeah? It's the same. Yeah? Same one. If we start with another position, yeah? P equal p over 4. Yeah? So this is the result in 3 dimensions. The trajectory of the points and that converts to the origin. Okay. Rotation and n-dimensional space. So this is a rotation and this is the composition of rotation matrix and this one composition composition matrix rotation with Rn is equal to this one. This is we have n by n matrix and at the position Ig, this is the Eig cosinus and this is minus and this one. So we have rotation matrix and n dimension. And okay, this is this n dimension. So the structure is the same, but now we have an n dimension. Rn is rotation matrix and n dimension, and R is scale. Okay, this is the problem is this is the restricting function. So we have here 30 dimension. So with m equal 100 and k equal 1000. This parameter we obtain that this one, but you see that the output is not satisfied because the result must be 0. But we see that the dimension is quite high. So it is must normally we start with not only 100 but more points maybe. So but it's this is the result. Almost closely to 0. Not 0. And the exact value is 0. So okay. Now another problem is finding roots of system of nonlinear equation. So before we talk about optimization, now we want to find root of system and using optimization. So okay, maximization of sorry. So we have a system of nonlinear equation. So you see we have n equation with n variable. So with equation with n variable with d equal to this one is the domain of the function and the bounded domain. The above system has a solution at x precisely when the function f(x) defined by this one is equal to 1, maximal value 1. So this is the what we call merit function. So merit function. So instead of solving directly this system, we transform the problem of solving a system of nonlinear equation, this one, into the problem of minimizing the function f(x), the merit function. So we define the merit function. This is our one definition. We have another. We have another typical definition. For example, we can say f(x) equal to square, summation of the square, or also summation of absolute value of ti. So this is another strategy. But in this work, we use this one. This number one. So this is as an example. See, basically, non-linear system have much more than one roots. For example, this one. For this is the first function and the second function. If we make a plot and XY in the XY for example in the contour plot. See, we see that this is the first function and the other function is one. So we see the intersection, and this is in the intersection. The point intersection are the root of the system. Yeah? So we see that we have here 12 roots. Yeah? Some of them is very close to each other. Yeah? So now the whole problem is to find these roots of the system. Yeah? Naturally, method we know that one can use a Newton method, Prudent method like that. Yeah? This is the exact method. Yeah? Also the gradient method. Yeah? But today we use another strategy to find the optimization. Now there is another function. And this is the 6 equation and 6 variable. Yeah. If we use the 6 plus this one. Yeah. Now, if we perform the one spiral optimization with 500, is this one parameter of spiral, we obtain this solution using the spiral optimization method. And we see that our merit function is equal exactly to 1. And if we substitute this one to gx, we have this one. Yeah, this is the computational, but it's not equal to exactly 0, but it's very, very small. Okay, this is now. The problem with this equation is like that. If we use, for example, Newton method or one spiral optimization method, we can find only one root. At its use the Newton or spiral or projection method, we only obtain one root. But the problem is, can we find all the root in one source? And our problem is, if can we find a method to find all these roots in one run? So this is not one by one, but in one run. So we want to talk about this one. So this is our clustering technique. This is the clustering technique. Now, suppose that we run a visual optimization. So suppose that we have 100 points, this one, and we want to find the minimum, the points of minimum. This one is 0. If we just run, so we have we have a root. The number, the function f and merit function will equal to 1. So not all these points. This is if we randomly this point, we search this point, we put this point, we cannot find or we cannot see where is the roots. But the indication is one, if we have a point near the root, not exactly in the root, and the function value will be close to 1. Because we have a merit function is between 0 and 1. So the greatest one is at the root. So if we cut this point and cut off, so if we, for example, we retain only point where the value of f is less than greater than 0.5, misalkan, like that value or 0.8. So we can only small number of points instead of all the points. Because the other point is must be distant from the roots, and for the point near the roots, so this might be satisfied with number of the value of merit function will be close to 1. So exactly that one. But it is not the exact position. Maybe the exact position on the root is at this point or this environment. So from this one we perform this one clustering. This is the clustering. We start with a point where the f value is minimal, yeah, among this finite point, yeah. And then we set the other point, yeah. Okay, yeah. So this is another the second point where the value is less than greater than this one, yeah. But this is the f, yeah. We divide this one and the middle, yeah. We take the middle point, yeah. This is the new point, yeah. We compare it with the value, yeah. So this is the circle, yeah. We want to find the cluster, yeah. So there is one, yeah. And like this one, yeah. Yeah, so we see that another point, yeah, this one, yeah, this, yeah. And next, yeah, divide the midpoint between the last one, yeah, this, and the nearest point from this one, yeah. And this one, yeah. We divide by 2, yeah. And this one, yeah, might be this one, yeah. Okay, yeah. This one, yeah. That's the technique, yeah. And until we have all the last one. So we see that actually we have this cluster, yeah. This is we hope that the real roots will locate in their position, yeah. So this is one. Okay, yeah. So this is the algorithm, yeah. So might be very complicated. So the number of source point at the clustering phase, yeah. This is the cutoff parameter, yeah. This is the very important parameter, yeah, to cut off the points. For example, if we generate 100 random points, yeah, and we must cut off those points, yeah, and we return only those point with greater value of f, yeah. For example, near 1, yeah. So cutoff parameter, yeah, and parameter for roots acceptance, yeah, parameter for differentiate one candidate and another, yeah. So we can differentiate if, maximum iteration number and exactly. This is clustering phase, yeah. Generate randomly initial point, yeah. So visible region, yeah, and k1. So set x star as x star, yeah. This is the maximum, yeah. The maximum of equal to 1, yeah. So a center of the first cluster, yeah, equal to, yeah, this is 1, yeah. And for E equal to this one, yeah. This is the cutoff point, yeah. Cutoff, yeah, cutoff point, yeah. Cutoff number, yeah. Maybe I also got the cutoff parameter, yeah. So we return only xe that is the value f greater than gamma, yeah. So we have much reduction of the number of points, yeah. And this one, this point will be considered as center of the cluster. Then maybe have a possibility to become a cluster center, and then do the following function cluster, yeah. So yeah, this is the detail, but maybe yeah, so it's very detailed, yeah. So example, basically, so with midpoint like that, yeah? So midpoint. Yeah? So we see that this is the midpoint between A and stress. Okay, yeah? And the differentiate, yeah? Okay, yeah. Set update, yeah? 2k times of step. Spiral optimization phase. So we use a spiral. Yeah? We have done step. We obtain a set of cluster. Each member of the set is the center and radius. To each of these, we perform spiral dynamic optimization to obtain a candidate of root at each cluster. Yeah? So this is the cluster, yeah? And selection of point, keep only candidate root which satisfy condition. This is the condition that fx is a root, so fx must be equal to 1. Yeah? So but this is a metaheuristic algorithm, yeah? So might be it is not exact points, yeah? But this point is very close to the exact root. So we return only candidate root which satisfy f is greater than 1 minus epsilon. Yeah? So we got a small number epsilon. Yeah? So we might be said this one is very near to the root. Yeah? Suppose from the set we get a certain candidate, then we show selection root. So very, yeah. If two roots are very adjacent and very close each other, might be those roots is only one number, might be, but so but might be actually there are two numbers, yeah, different, two roots different, yeah. Where is that? So yeah, yeah. Okay, yeah, I'll select the point, yeah. And root x of system one. So we have this is another one. Another feature of the method is we propose instead of pseudo-random number, because the pseudo-random number may not uniformly distribute in the specific region of the problem. It will be helpful if it is possible to generate population of points in the set region for which the deviation from uniformity is minimal. So we talk about this one. Suppose we have a set of points. So yeah, this is the discrepancy of set of points. So it is not mentioned there. When the set of rectangle is also, yeah, this is the construction of Sobel sequence of points. And the low discrepancy sequence, and you know, and the more equivalent the points of the sequence are distributed, closer discrepancy of it. So this is the Sobel sequence. So this is very detailed. So might be I would guess visual comparison. Scatter plot of the first 100 points. This one is Sobel sequence of points. This is a construction of Sobel points are not random but deterministic. So there is an algorithm to construct this Sobel sequence of points, quasi-random. And this one is one of the point generated using a pseudo-random number. So we see that we have some area where there is no point. We can no points here. But you see that using Sobel sequence, almost all position will be at least 1 point. So the points will be distributed more uniformly than pseudo-random. Okay, so this one, this feature is very good if we want to find all root of the system of equation, because the root of the system might be greater than 1. So the point in the space is difficult to find, especially in higher dimension, and dimension greater than 3 or 1, where we cannot find the picture. So we must find. So the Sobel sequence of points they contribute greater enhancement from the method. So as a numerical experiment, you see this is the interesting function analysis. We see that this is the definition of Weierstrass function. So this is n equal to 1, the infinite. This is the function. S equal between 1 and 2 and lambda greater than 1. It's known as a function. This is a famous function which is continuous but nowhere differentiable. So this function is not differentiable nowhere, but continuous. So if but and also suppose that we cut the n only for n equal 20 with s as 1 and lambda equal to 1.5. We truncate the summation only 20. So this one, this is the equation. Now we want to find the root of this function, gx, the subspace between 0 and 5. Okay, this is very interesting, because if we plot the function, first use the clustering technique. The input, this is the clustering, this one, the spiral optimization. We see that generate Sobel sequence with 200 points, and K cluster, K max, 5p, epsilon. This is the if it was a very small epsilon, and delta to differentiate if 2 points as very near as 2 points as root or only one root. So it would difference the problem. And this is spiral optimization for each cluster. So we can this one. And this is a very interesting result. Using clustering technique and spiral optimization, we found 9 roots. You see that x1, and this is the root, and this is the value of g, almost equal to 0. And you see that this one is very, very close to each other. 3, 4, 5, 6, and 7 is very close to each other. We divide at the third digit after this one. It is one. So, look at the plot on the graph. This is the Weierstrass function with n equal to 20. This, if we plot the function, we see that we only have this 0. 1, 2, 3, 4, 5. 5, 1, 2, 3, 4, 5. Using visualization. But actually, this point, if we perform the zoom at this position, we see that we have more than 1 point. So instead of 1 point, we have 1, 2, 3, 4, 5. So 5 points and generate into the 1 point, 4 points. So this is a really root of the system. This equation. And this is confirmed using this one. So the number. The 0.345 difference at the third digit after this one. So very close each other. Root is very close to each other. And our method is can differentiate this point. So using clustering, this is the result on the clustering technique. So we can obtain 9 root instead of 5. From figure we see that on the 5, but really this one 9 root. So this is another example. This is this one, a nonlinear system. If we use clustering technique, 2000 and spiral optimization and so on. Okay, now we found all is 12 roots. This 12 root is obtained in one single run. You see, using pseudo-random points, we have found simultaneously all roots in 6 runs from 100 runs. So if we have at the start we using random number instead of so-called sequence, we see that in 100 runs, we perform 100 runs. Simultaneously, we found 12 roots only in 6 runs. But in the methods, spiral optimization using clustering, we found 12 roots in one single run using the parameter of clustering this one. So we have 20. So using this parameter, we obtain 12 roots at the single run. So we see that G is almost equal to 0. This is not 0. We see that we can find all those roots, 12 roots. So this is very, very close to each other. This one is we obtain in one single run. Not one by one, but single run, using clustering. This is this is in the base is contour plot, and this is the value of f, and the value of merit function. So in the 3 dimension, and see we have input this one, and this clustering technique. So okay, sorry, in Indonesia. Okay, so I would like to show you this one. Yes, now this is the first running. We with 50 points, and among them, this one is the highest point, the highest f. So we distribute this point the same sample sequence, 50 points, and one of them lie in this one. So we see that this is the contour plot, and the yellow one is the highest value of merit function. So naturally, the root will be situated in this area. So this one is so we can say that run the program. This one, so this is one. Okay, this is the process of running. Using spiral optimization. So okay, and convert to the root. So this one. Okay, this is one root. So I see. Actually, there are 12 roots, but I see this is the second one. This one. Second one. Okay. So this is another point. So we see that. Okay. This is. Okay, second one. Oh, this is the first one. Sorry. Oh, this okay. This is a small problem there. Okay. Okay. I saw that this one is another point. Okay. This is we found another one. This one. We see that this is another point. Start from here and we found another point. Good one. This one. So we have only one solution using spiral optimization. Okay. Now this is another function, and this one is equal to. Okay. Okay. This one a clustering technique, and this is no function. Non-linear function. Instead of solving directly three equations, and we perform a substitution. So we have two functions, and this one is okay. Then this one is equal to okay. This is actually a 9 root. This one, and we found this one. So exactly. This is the one. Another point is we have 6 variable clustering technique. We found that we have 2 roots. We have this is a new root because in our and of my reference this is one only a paper only find this solution and we have another solution using cluster. Okay, so we can also find the complex root for the system. So this one, if what about the complex root? So this one is complex number and complex function. So basically, if we have a complex function, we can separate in real component and imaginary component. And this one, so we can find real and imaginary. So we separate imaginary part and real part. So basically, we have 4 equations and 4 variables. So you can find using the spiral optimization. Okay, you can find. But it is not always easy for a given component to, especially real and imaginary part, working directly with component. In C++, we may use library complex H, and this one is a sample using the C++. Okay, with simultaneously this root. Okay, so this is one. This one, not problem. Okay, this is very, we obtain 6 real roots and 21 complex for this problem. This is we have 3 problems. This one, and there's 6 roots, real root and 21 complex root. This is the real roots and 21. And the other problem is 2 roots and then complex root. Yeah? So we can also the Diophantine equation. Yeah? Suppose an among variable must be integer. Yeah? Before calculate merit function f, we must convert x1 xe to become integer type. Yeah? F is binary. Yeah? So this is the same technique. Yeah? For example, this one, the solution must be integer. Yeah? For this one, yeah? Using clustering technique, yeah? With this parameter, yeah? We obtain this one. Yeah? This is the function. Yeah? And okay, yeah? This is another Diophantine equation. Yeah? That is that. Okay, yeah? So we have solution. Yeah? Okay, yeah. Okay, that is one. So, so there is another application of mixed integer nonlinear programming. Yeah. So this is yeah. The real problem is the real problem. Yeah? Speed reducer. Yeah. So yeah, the problem is mathematically the problem is like that. Yeah? This is the function, the objective function, and subject to yeah. This is the constraint. Yeah? Nonlinear constraint. Yeah? We have 11 constraint. Yeah? And among the variable, six variable, x3 is must be integer. Yeah? Among the 6 variable, x3 must be integer. Yeah? So using technique, yeah? Using penalty function like that, yeah? We have output this one. So it's exactly the same as on our reference, yeah? Benchmark function. Yeah? This one, yeah? Our method will give this one, yeah? But our benchmark function is, but it's okay. Yeah. But this one is using another technique, yeah. So this one, yeah. Okay, is in the same, yeah. This is the problem, yeah. This is the optimization problem with constraint, yeah. So this one, yeah, constraint, yeah. But now we have the x1 and x2 must be multiplied of 0.06. This one, yeah. So this okay, yeah. Makes sense. Integer programming. Okay, yeah. So this one. Another point is relative problem. Yeah? This is the end problem in sport. Yeah? Relative problem. Yeah? We have for sprinter, one of which yeah, for this sprinter are selected randomly, yeah? From group. That this one. Mathematically, this one. And the problem is 0-1 programming. Yeah? This is the 0-1 programming. Yeah? This is the minimize this one. Yeah? And constraint, and this is the 0-1 programming. Yeah. Okay, yeah. This is the data. Yeah. For example, yeah, we have 6 sprinter, and we will sort among the 6 sprinter. We must find 4 of them. Yeah, in the fastest, the total fastest fraction of this one. So this is the data. Yeah. And using spiral optimization, yeah, this one. Yeah, we obtain this result. Yeah. Okay. Yeah. Fraction 1, absolute 3, number 3. So the total time is this is a good one. So another point is we can find also the problem sorting. This one, this is the technique. Okay. Multimodal optimization. Yeah, this one is if we can multimodal. Instead of finding root, we can find multimodal optimization. So this one is the example. Using the this is the spiral optimization, intervention base. We obtain this one. 5 results. The 4th one is the minimum, and the last one is the maximum. So this one is minimum and maximum. This is okay. Yeah, this one. Okay. Yeah. This is another step. Diversification phase. Yeah. Okay. Yeah. So this is the standard problem. Yeah. Restoration using exact method. This one. Yeah. The difference. Yeah. This is stationary point. Yeah. Okay. Yeah. Exact. So basically we have the spiral will be applied to this point. Yeah. See, stationary point, and so we can find the root of this point. Yeah. Okay. Okay. Yeah. So we have done. Yeah. So this is the point. Yeah. So we can. Okay, sampai conclusion ya. Yeah. So the root finding problem has been transferred to global optimism problem. So instead of directly finding roots, we perform the problem transform to the optimization problem using a combination of the proposed clustering technique and spiral optimization algorithm. The roots of the system of nonlinear equation can be localized and identified in single run. So the result from various test cases indicate that all real can be found without a priori, without a priori knowledge of the number of the roots. So in general, we cannot state how many roots for a given system of nonlinear equation. So this is the great problem in finding the root of system on nonlinear equation, especially in higher dimension. We cannot find how many roots. Maybe some is the multiple roots and like this. So to improve the openness, especially for ND, setting the parameter of the algorithm must be carefully done. This is the problem with metaheuristic. It depends on the choice of parameter. A modified explanation algorithm may be used to solve MNLP problem mixed integer nonlinear programming. The use of sample sequence of point instead of pseudo-random to generate initial population of point from the may enhance the effectiveness on the method. Okay. Combination of the proposed clustering technique and SOA have been shown able to obtain the maximum and minimum point, both local and global, of the multimodal function in a single run. So this is the result, and this is the reference. This is the first paper from Tamura and Yasuda. This is the first time the spiral optimization algorithm is introduced. And yeah, this is our paper, finding all solution. And spiral, and this is the solving mixed integer nonlinear programming, and the third point paper. And also we're finding multiple solution of multimodal optimization. So we find all multimodal optimization using spiral optimization and component compact roots. So we have some, and yeah, the recent paper written by Novriana and team and Ayam and Kanya, etc. This is the method of finding numerical solution to Diophantine equation using spiral clustering. This is a variation, variation publication. So this one. Okay, thank you for your attention. Okay. Yeah.
Thank you very much, Professor Kuntjoro. It is very interesting talk. Before we go on with the question and answer session, we want to relax first and to hear the song, any song. Professor Edi, silakan.
Okay, thank you, Bu Ana. So now we are going to present some song. This is a dedicated song for Pak Kuntjoro. So this song is sung by our alumni of choir group of ITB, and two of them, the singers, Pak Kuntjoro will recognize them.
Thank you.
Let me share. Sorry. Just a moment. Okay, I stop first. Okay, I should share. Okay, the sound is shared already. Yeah. Okay.
Oi, Bapak tuh. Okay. Timur.
Langit memiliki kuasa,
Okay. I hope Pak Kuntjoro enjoy and everyone here enjoy the song. Pak Kuntjoro, did you recognize some of our colleagues there?
Yeah. This is Rino and saya.
Okay, good. Excellent. So back to Anna.
Yeah, Rino is a PSM, member of PSM.
Yeah. Okay.
Paduan Suara Mahasiswa.
Okay, thank you very much. There are Ibu Rino and Ibu Hilda from Singapore.
Yeah. Thank you.
Okay, now we want to have answer and question. I will take a look at in the chat. There are 3 questions from Bapak Muhammad Lutfi Syahab. Bapak Lutfi, do you want to ask that three or I just read it?
Okay. The first question is, how do we determine the number of clusters?
Yeah.
The first one is, how do we determine the number of clusters?
Okay. We cannot in advance know how many clusters we will obtain. So this is we cannot answer this number in advance. So it depends on the problem. So and also you can see that we use a cutoff parameter. So if we have a cutoff parameter gamma is lower, for example, if we have a gamma is equal an OR experiment, if gamma is taken as, for example, 0.8, this is very close to 1, almost we cannot find a point which satisfies at this condition at the primary phase. So it is advisable to use the gamma a lower value, for example, 0.5, 0.1 and 0.5 instead of 0.8. so 0.1, and so we have some points that eliminated from this one. But the number of cluster cannot determine any function. So it's depend on or heavily on cutoff parameter. Yeah? So this is not the problem. Yeah? So okay. Yeah?
So we just decided on the number of our cluster. Yeah, we just self-divided. Yeah.
Yeah,
We
yeah.
determine
It's
10, or if it is not sufficient, and then we have addition number of clusters, something like that. So Professor Kuntjoro said it is depend on the question. Yeah, equation. Yeah.
Yeah, yeah.
So the second question is, how efficient is the method for solving non-linear systems?
Yeah, okay.
For example, with 100 variables and 100 equations.
Yeah, this is the question that I will ask every time. Yeah? The problem with this method is really heavily on the what we call the rotation transformation. So with mapping, rotation mapping. Yeah? So if we have higher dimension, we must perform several projection matrix. Yeah? So this took a lot of time. Yeah? Up to now, I've worked with only under 45 equation and 45 variable. Yeah? Over that is very time consuming. This is the problem. Yeah? So this is open. Yeah? This is the problem with the method is the number of projection matrix. Yeah? So this one is rotation matrix, projection matrix like that. Yeah? And higher dimension, we have so many projection matrix. Yeah? So on the method will be not efficient. Another point is we can use parallel computation. Yeah? Instead of sequential, yeah, to perform analysis in each cluster we have found. Yeah? So and in this environment method, yeah, we have used sequential procedure, yeah? Sequential, not parallel processing, sequential optimization. Yeah? But one of my students in computational science, yeah, I took to use parallel computation for this technique, yeah? And he success of it. Yeah? So the computing time will be very reduced, yeah? Using parallel computation, yeah? To perform optimization in each cluster. Yeah? So for example, if we have 100 clusters, so yeah, if we one by one, yeah, to time so longer time. Yeah? But using a parallel computation, we may reduce the time of computing. Yeah? So this one is another problem. Yeah. Okay, this one is the problem is the method is if we have a higher dimension. Yeah? Up to now, we have success with 45 variable. Yeah?
Okay, the third question is the method good for optimizing machine learning problems?
Basically, if we have optimization, yeah, so we can use this technique. Yeah? For example, recently we have worked on maybe a new method in solving a partial differential equation, physics-informed neural network. Yeah? Or maybe some people, yeah, this is a kind of physics-informed neural network. Yeah? And also we have used this technique to solve the differential equation or partial differential equation using physics-informed neural network. Yeah? Basically, the method is we perform the approximation function using artificial neural network. Yeah? And after that, we use the physics-informed neural network. This means that we minimize the loss function. Yeah? This is the loss function is the approximating solution found using neural network. We perform to the differential equation, and naturally, and also it's boundary and initial condition. Naturally, we have a penalty function. So we have the loss function. So we have to minimize those loss function. Normally, in the literature, people use the Adams, Adams, adaptive differential method to perform the optimization. But we have tried to optimize using spiral optimization for this problem, and succeed, especially in the problem in finance, the differential equation like that, and for example, in Black-Scholes equation, this is the second order partial differential equation, and we solve using the Penn method. This is okay. Yeah, this one is pretty important.
Okay, thank you, Professor Kuntjoro. The second person who asked is Mr. Said Etsa. He wrote that, thank you for the explanation of the material provided. There are a question or discussion. What are the prospects of this method if hybridized with other methods? So it is mixed with other methods. How is the prospect of this method?
Okay, this is a good question. For example, when solving a system of nonlinear equation like that, we have found, you see that we have, this is like, basically our method is metaheuristic method, but really, and the method if we use the Soppel sequence, all procedure is deterministic. Yeah. But if we use pseudo number in the first at k equals 0, so the method will be metaheuristic. But in our technique, we use, instead of pseudo number, we use a Soppel sequence of point. So under the same set of parameters, we if we run several times, we have left at the same solution. But if we use a pseudo number, we have different solution. So we have solution. Okay, so if we found using this technique, the solution of the roots, this is you see that approximately this is only the what we have found, we call this nearly optimal solution. So this is what we call because a kind of metaheuristic, near optimal solution. It is different. For example, if we use Stephenson method like that. So the stopping criteria is a gradient equal to 0. So this is the exact method. Okay, and in that situation, we can hybridize. So we perform first, especially in higher dimension. Because in higher dimension, if we use the exact method, it is very sometimes it is not easy. Especially if you have using Newton method and Broden method like that, exact method. The problem is we must calculate the gradient, and also we must supply with initial points, with hopefully close to the problem, close to this exact solution. So this is the problem. If we are not exactly near the problem, maybe we trapped in the local minima. But okay, but another problem. Only minima will be global optimum. So this is using the merit function like this. All the 0 is global optimum. So this one. Here we can use after perform some spiral run. Maybe it might take time, and we hope that the solution will be almost close to the real roots. So we can continue using the exact method like Newton or Broden like that. So this is the hybrid method. Spiral optimization may be used to find the good initial quest for the exact method, and that at the final step, in the final method, using the exact method. So we hope that we have a much more accurate solution. So this is the hybrid method.
Okay, and the second question is very specific about how to mix the method with machine learning or neural network problems. What is
Yeah.
the prospect?
Yeah. I just stated about the problem. Yeah. As especially, yeah. When you have a minimization problem, yeah, like that, machine learning at the end it must be deal with optimization. Yeah. When we have an optimization problem, basically we can use, for example, the spiral method, yeah, to find the global optimum solution, yeah, or another technique, yeah, metaheuristic. Yeah. But especially for the root of finding a solution, root finding, here's the problem. Yeah. So that is the issue to machine learning or neural network problem. Yeah. So I just talk about the PIN, PINN. Yeah. This is the new method, yeah. Physics informed neural network. Especially in I would talk about the problem, yeah. And engineering problem, yeah, like that in petroleum engineering, yeah. We use analysis of the reservoir, yeah, to perform the drilling is very high cost. Yeah? So to analyze the NDR, yeah, given area, it can not use multiple drilling method. We can use on several drilling problem, yeah? And that continue using PIN, yeah? Physics informed method. This is the problem using first initial approximating solution you perform using artificial neural network, yeah? And then the second phase is to use the physics informed method. This is the solution must be conform to the problem. Yeah? So this is must be solution of the differential equation and its boundary and initial condition. Yeah? So the problem is to minimize the penalty function, which consists of objective function. This is the loss function of differential equation, the residual function, and plus boundary and final and initial on the final condition. Yeah? So this is the optimization problem. Yeah. So
Okay. Yeah. Thank you. The next question is from Mr. Ayumi Sasmito. He is wondering whether the metaheuristic algorithm is used as a comparison of this problem and how it is resolved.
Yeah, all of the example I have shown to you, this is taken from another paper. Yeah? So this is another paper. Yeah? And the paper is use another method, naturally. Yeah? So we compare with this paper. Yeah? Some is a good solution, and another is the other paper they found only one, and we can find another solution. Yeah? For example, this one, yeah? Because we use the clustering technique, yeah? Especially in higher dimension. Yeah? So this when is comparison, yeah. But the problem is in higher dimension is naturally all example is be treated the dimension not so higher, maybe the 10 dimension, 20 dimension like that. So the other paper is using the metaheuristic like genetic algorithm on PSO, to solving the problem. So and the result is also comparable. Sometimes we have better than the result obtained from the other paper. So, okay. All the example we have shown to you. This is I took from problem of the other journal. So we have a comparison. Okay.
Okay, thank
especially
you.
For the but not for the complex root, because also not so many journal produce the complex root. So yeah, but we found that one. Okay.
Okay, thank you. And this question from Mrs. Irma Palupi. Thank you for a very clear and excellent presentation. I'm interested to how to implement this method if we have mix of discrete and continuous domain. What is acceptable?
Okay.
Good idea to do rotation in discrete space. Thank you.
Okay. Yeah. Maybe this might be. I think what you mean might be is mixed integer nonlinear programming. Maybe this is the problem of minimization where the variable is some variable must be integer, and the other might be real, yeah? So continuous, and some variable might be discrete, yeah? Or maybe or another problem is 0-1 programming, yeah? Or mix. Some variable might be 0 and 1 value, and another must be integer, and the other must be real. Yeah. So we have mixed integer non-linear programming. Yeah. We have we have solved this problem using this technique. Yeah. Sorry. Yeah, we have solved this problem also, yeah? Especially mixed integer non-linear programming. Yeah? So there's no problem. Yeah? This problem. Yeah. When we want to, when we arrive at the step of finding solution where some of the variable must be integer, for example, yeah, yeah, our algorithm run in a real variable, yeah? So in the continuous one, yeah? And we must make adjustment. Yeah? So we must reduce to the nearest integer, or nearest integer. Yeah? So to tackle the problem with integer programming, we have a real solution, and we translate them in the rounding this solution, yeah? And perform the next step. Yeah? So there is a problem. Yeah?
So in fact, we have this implementation to the discrete. Discrete means that we want to find the integer solution,
Yeah.
but actually we do it in continuous, continuous space, and after that we look for the integer one. Yeah, something like that. Yeah.
So we can.
Okay.
Okay.
Thank you for who like to give questions. I think the time is up. So thank you very much for Professor to give the excellent presentation, and then I will give it back to Professor Adji. Thank you.
Okay.
Okay, so thanks again. Yeah, let us join me to thanks to Professor Kuntjoro Adji for wonderful and inspiring lectures today. And on behalf of the Faculty of Mathematics and Natural Sciences, we would like to present you some certificate, Pak Kuntjoro.
Yes, thank you.
A kind of small token from us, from the Mathematics Distinguished Lecture Series.
Thank you very much.
Let me show you the certificates.
Okay.
Okay. Yes.
Okay,
so
yes.
this is the certificate of the Mathematics Distinguished Lecture Series presented to Professor Kuntjoro Adji Sidarto, signed by our Dean, Faculty of Mathematics and Natural Sciences.
Okay, thank you. Thank you very much.
And also, this is appreciation. So our, we like to thanks to Professor Kuntjoro Adji for giving these lectures. Yeah, and this is done by not spiral optimization, but by AI. AI apps. Okay, we will frame these nice photos, and we will give you in person, Pak Kuntjoro.
Okay, thanks.
Okay.
Thanks,
This is from our Prodi, our mathematics department. Okay, so again, thank you very much, Pak Kuntjoro, and thanks to everybody for attending this lecture, and see you again next month. Yeah. Okay, bye-bye from now. Yeah. Terima kasih semuanya. Ya, wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam.